Great. Well, thank you very much all for coming and welcome to this session. Just a quick bit of housekeeping to start with. So obviously cameras and microphones off, please, to make things easier for everybody. We will be recording this session and the recording will be made available afterwards. Please do place messages in the chat if you have questions for our speakers at any point. We will have time to get round to those. And we will also be posting kind of useful links in the chat as we go through. This session is going to cover two things. So we're going to be looking at the Western Power Distribution Data Science Challenges, the previous competition, so competition 2, with kind of the results from that and presentations from the top 2 teams, and then kicking off our third competition to kind of see what we can come up with next. So let me kind of cover that. We're going to have a quick introduction from Liam from WPD, a recap of what Challenge 2 was in case you weren't involved with it, those presentations, and then the kind of kickoff for the final challenge. So over to you, Liam. Off you go.
Yeah, thanks for that, Sam. Yeah, so Liam McSweeney, so I'm the data science lead at Western Power. And I suppose the level of interest in our first kind of data science challenges was, I'd probably describe it as incredible, I think. So kind of knew we had to keep this, keep them going and make them a regular feature. So we're hoping to do more of these in the future. And as everyone knows, making our data open is all about using it to kind of add value and benefit to our customers and stakeholders. And as part of all of these challenges that have been run in conjunction with ESC, they are all real world examples that we are trying to work out internally. And I think that's what I enjoy so much about looking at the results that come back from the analysis that you guys have done, that, you know, it does come back to tangible business benefit, as well as creating a sense of community around data science. And yeah, we're just super happy with the way these things have been going along. And yeah, hopefully, and well, not hopefully, but definitely we'll be doing some more of these in the near future as well. So watch this space, I think. Thank you very much.
Thanks, Liam. And there's, for people who haven't kind of been involved in much detail before, there's been kind of quite a lot of work coming out of these challenges, kind of lots of participation from quite a range of teams, papers being published, and we're building up a community on LinkedIn, which we will post the link to so you can join if you're interested. The challenges are designed to be 3 challenges over the course of a few months, and all of the problems, as Liam said, are kind of real world WPD problems, and this is the kind of like second challenge that we're presenting the results for. So let me give you a quick overview of that challenge. The basic context is there being increased uptake of electric vehicles as we kind of move to a low carbon economy, and as we have networks needing to provide charging for those, we have the challenge of like, how do you work out how many EV chargers are there on the network? And so this challenge was constructed in a way where if we are monitoring primary substation demand, can we detect the embedded EV demand as a result? And so the key aim of the challenge was to predict the biggest daily increase in demand at kind of like 15-minute resolution on primary substation feeders that was driven by EV usage. So kind of looking at it graphically, we had the substation raw data in green, we created a kind of blue curve using actual EV data, combined the two to produce a red curve. And what the challenge participants needed to find was that kind of like, what is the orange line? What's the kind of maximum daily load due to EVs as a result? The data that was provided, all kind of real world data. So there's 2 years of half-hourly demand data for 6 substations, EV charging data, and then weather data from 9 sites. And the kind of metric, the way that we were scoring was root mean square error, but then normalized by a simple benchmark, where we basically assumed that the non-EV demand is the same as the week prior to the test period for kind of like all 8 weeks. How did people do? Well, very well is the answer to that question. We had a lot of submissions, a lot of different teams, and some really impressive results. And so kind of skill scores of 0.24, kind of significantly beating the admittedly quite naive benchmark on that. So it'd be really interesting to hear from people kind of how they got on. And so that's what we're going to cover next. So first, let's hear from team WOJJ and Jemima. So Jemima kind of earned her MSc in theoretical physics at Imperial College London, and then moved to the electrical engineering department to start a PhD looking at distributed learning for probabilistic forecasting in energy systems, with a particular focus on privacy preserving techniques such as federated learning. And during the first year of her PhD, she focused on inertia forecasting in the Nordic, but now has kind of moved on to consider forecasting related to electric vehicles. And so this is then very relevant to her. So Jemima, over to you.
Great. Let me just share my screen. Can you see the presentation? Ooh. Okay, great. I'm going to assume you guys can see it. So I'm Jemima, and I'm presenting on behalf of Team WOJ, which is also Wang Kun, Ola, and Jack. And we're all PhDs at Imperial College London. So today I'm going to talk about the different approaches we had for this challenge: data exploration, feature engineering in phase 1 and phase 2, generalized additive models, which is what we used, R models specifically, and some brief results. So there were 2 approaches we tried for this challenge. So the first was to forecast the base load and subtract that from the combined load to get the load from the EVs, and then work out the maximum daily load from EVs using that. And the second approach was to cluster EV profiles and feed this into an LSTM. So you can see some of our clustering on the right-hand side of the screen. We used k-means clustering, and you can see the left column is all the different EV profiles, and the right column is the average of each of those clusters. We found that the clustering approach didn't perform as well as approach 1. And we think this may be because the EV profiles were over a different time period to the time period we were considering. So from then on, we focused on approach 1, which was forecasting the base load. So on the screen here, you can see our visualization on the left, and there's a QR code that you can scan, or there's a link in the bottom. I think if you use Chrome, Firefox, or Microsoft Edge to view it, it works best. And you can see it on a mobile, but I think it looks better on a computer with the pop-up graphs. But basically what we have here is a plot of all the different substations and weather stations. And you can see the name by hovering over it. And if you click on it, you'll be able to see some of the graphs linked to that substation or weather station. The weather stations show the wind speed data, but unfortunately there isn't space on the slide to show that. But more importantly, the substations show the load, both the base load and the combined load over different time intervals. And that was really important for our feature development because you can see that there's an annual periodicity and a daily periodicity, and we really wanted to capture that in our model. So when we were doing feature engineering, we created a month feature, an hour feature, and a feature that was either a weekday or a weekend. So we split the two because obviously there's different behavior seen in load profiles depending on whether it's a weekday or you're on the weekend. Also, so if you are following along on the visualization, if you have a look in the top right-hand corner, you'll see that there are lots of different layers that you can apply on top of this map. And each of the different layers is named after a different substation because it will show you the data we've included for the model of each substation. So we obviously use the load from the substation of interest, which is the one highlighted in dark blue. So if you have a look at the figure on the screen right now, this is for Portishead Ashlands. You can see Portishead Ashlands is highlighted in dark blue. And we also consider substations within 40 kilometers, the load from those substations. So there's a 40-kilometer radius drawn around in dark blue, and you can see that some substations are highlighted in light blue, which means that we consider those. And we also consider weather data from the nearest weather station. So that is also highlighted in light blue as well, if you're following on the visualization. Another interesting thing was that we found that when we just used the raw weather data, the model didn't perform very well. So after doing some investigation, we found a paper by Larson et al. That's referenced at the bottom of this slide, where they applied single exponential smoothing to the weather data, and that really improved results. And we found the same thing as well. And then in phase 2, we applied temporal encoding. So we changed the feature of whether it's a weekday or a weekend to a feature that looked at what day of the week it is. And we applied temporal encoding to that because that had worked really well for us in data challenge 1. And we also applied some smoothing to the load 56 days before, both at the substation of interest and the substations within 40 kilometers. And we also applied weighted smoothing to the national demand, and the national demand was additional data, open source data that we were all allowed to use that was added later. And the reason why we decided to apply this smoothing is because if you look at the graph on the right-hand side of the screen, you can see that the ground truth data shown in green is quite smooth compared to our prediction shown in orange, which is fluctuating quite a lot. So we wanted to smooth out some of our features to try and get a smoother prediction. So these features were used in a generalized additive model, which is quite a simple model. It's just a sum of smooth functions like splines or tensor products. And we ended up using quite a few tensor products to try and capture the interactions between different features. And also because it allows us to combine features with different units. But one thing to be careful if you are using a generalized additive model with tensor products, the order of the features matters because you're dealing with tensors. So the benefit of a generalized additive model is the fact that it's quite interpretable. But obviously, given that we've used quite a few tensor products, some of that interpretability is sacrificed a little bit. And one of the limitations of a generalized additive model is that you may not be able to uncover such complex relationships, although we have tried to add some complexity into the model by using tensor products. So our model ended up looking like this. So just to talk you through it quickly, I know it looks quite confusing. The first term is so all of these are tensor products. The first term is looking at the relationship between the base load at the site of interest 56 days ago, the month and the hour. The second term is looking at the interaction between all of the different periodicities we're considering. So the month, the hour, and then the temporally encoded day of the week. The third term is looking at the interaction between the month and the wind speed, the north and east wind speeds. And the wind ended up being the only weather feature we ended up using. We did have a look at the solar irradiance and the temperature as well, but we found that the model worked best with just wind. And then the final term here is a sum over all of the substations within 40 kilometers, because obviously you can have multiple substations within that radius. And we looked at the interaction between the baseload 56 days ago, the national demand, and the baseload at the substation within 40 kilometers 56 days ago. And we also looked at the interaction between the month, the hour, and the load at the substation within 40 kilometers 56 days ago. So that's a really brief overview of the model. If you're interested in seeing it in more detail, I've got the QR code for the GitHub repo. All of it is public, and there's also the link on this slide. So then finally onto the results. So in phase 1, we managed to get a skill score of 0.26. And our approach was actually to, since we were allowed to submit in phase 1 after phase 2 had started, we decided to keep submitting there and keep trying to improve the model there initially. So we got a skill score of 0.26, and when we sent that same model, when we applied that same model to the phase 2 data, we got a skill score of 0.29. So we were quite happy about that because it meant it wasn't overfitting too much on the phase 1 data. And then by applying the smoothing that I mentioned and the temporal encoding of the day of the week, we managed to reduce that further to 0.248. And you can see for Portishead Ashlands roughly what our prediction looks like. So thank you for your attention. I've got my email address on the screen, so if anyone has any questions that we don't have time to discuss here, feel free to email me. And there's also the links to the GitHub and the visualization, or there's the QR codes as well. So I'm happy to take any questions now.
Great, thanks very much, Jemima. If anyone has questions, please do pop them in the chat and I'll pass them on. The first one that we've got is, what was the kind of reasoning behind choosing 40 kilometers around a substation? Kind of how did you arrive at that?
So that was through trial and error. We tried a few different combinations of like different substations, different distances away, and we found that the best results came from having a 40-kilometer radius around the substation.
Great. People commenting on the kind of visualization and how cool that is, something that I second.
Oh, thank you.
I also have a question for me. What you ended up kind of temporal encoding the day of the week, but not the hour of the day. Did you try both? And if so, like, why did you end up with the kind of combination that you did?
Yeah, so we did actually try applying temporal encoding to the other features, but it took such a long time to train, first of all, having temporal encoding applied to other features as well. And then also we found that the results weren't as good. I think we tried looking at the temporal encoding of the month, and we found that the results got worse after it had taken hours to train the model. So we thought that it would be best to just leave it, because the reason why it takes longer to train is that when you have the temporal encoding, you go from one feature to two features. So a lot of our tensor products are groups of 3s. When you start to have groups of 4s, that starts to take a long time to train. And then if you've got lots of groups of 4s in tensor products, groups of 4 features, it can take a ridiculous amount of time to train because it's getting quite complex at that point.
And another question from the room, did you stick with GAM from the start, or did you experiment with different models?
So we did try some different models. I think GAM was one of the first ones we tried, just because it's quite a simple model. And then we did try, I think, some deep learning models as well. But we found that the GAM was performing the best, interestingly. So we're not quite sure why that is, but that's why we decided to stick with it. But it was actually one of the first ones that we tried.
Another question, what were your impressions with LSTM? Do you think it could still be useful if you had more time to engineer it?
With the EV profiles? do they mean, or like applying it to, because we had the two different approaches, one where we were forecasting the base load. Are they talking about applying the LSTM to that, or about where we clustered the EV data and then applied the LSTM?
I don't know, Jewel, if you want to, the first one, there you go.
The first one. I think we did actually try to use an LSTM with this. It may have been overfitting. That was the reason why it wasn't performing as well as the GAM. I think it's more likely to overfit, but we did actually try it, and it wasn't getting as good skill scores. So then we just left it.
Cool. And another question around, do you know how much influence the national demand had on the prediction accuracy when you kind of introduced that feature?
So I think there was a definite improvement, but it wasn't by a huge amount. Yeah, I can't remember exactly how much it was, but it was quite a small difference. And it's probably that the national demand is looking at like a much larger region. So it's not as specific, maybe. I imagine, I'm pretty sure the substations within 40 kilometers had a larger effect on the accuracy than the national demand did. But because it still had some small improvement, we decided to keep it in.
Great. What tools or packages did you use for the visualization? I guess it's another useful thing.
Yeah, so for that, I used a package called Folium in Python, which is a really cool package because it's very easy to use, and then it gives you a map visualization in HTML, so you don't need to fiddle around with any of the HTML yourself, which is quite nice. Great.
And final question, are you planning to kind of write this work up into a paper or publish or that kind of thing?
We hadn't discussed it, but that could be a nice idea, but I think, yeah, we haven't discussed it as a team.
All right, cool. Well, thank you very much, Jemima, and well done.
Thank you.
Great. And so we'll now be kind of passing over to Florian Ziel. So Florian is an assistant professor of environmental economics at the House of Energy Markets and Finance at the University of Duisburg-Essen in Germany. He received his MSc in statistics from University College Dublin and his diploma in mathematics from Dresden University of Technology, and his PhD in forecasting in energy markets from the European University Viadrina in Frankfurt Oder. His research interests include data analytics with applications to energy markets and systems, and he's the first author on various peer-reviewed journal articles, most notably top-tier IE transactions on power systems, applied energy, energy economics, renewable and sustainable energy reviews, and international journal forecasting. And he has lots of experience with forecasting energy demand. So Florian and his team kind of came first. So over to you, Florian. Interested to hear how it went.
Okay, so thanks. I think you should see my screen now. Yeah, yep. So yeah, thanks for the nice introduction. So everyone who joined the last time, yeah, they are really presented as well. And thanks for the nice talk from Jemima. You will see some similarities in this presentation. So this is a joint work with Jonathan Barish. He joined in the last and the first challenge as well, the team. But Michal, who joined last time, yeah, he just became father and is in parental leave right now. So we just did this task in a team of two. So what we did here is very similar to what we have just seen. So basically, we just used R and GAMS. So we have seen that generalized additive models can be a very suitable tool. So, and we used this as the main tool in the first competition as well, and there in combination with neural networks. But here we just stick to generalized additive models. We did not try something else. And I would say the main reason why we got, yeah, why this is here more suitable is because this task is more about statistics than about machine learning. And I think you might understand, I think why, at least I think so, in a couple of minutes. Okay, what we will do today is we first talk a bit about data pre-processing, and then we want to understand the model objective, which I think is very important to really understand what we want to predict to create a good model. And then afterwards, you will see the corresponding model, which is, as I mentioned, a generalized additive model. So the first thing is on data cleaning and data pre-processing. So we just had, so with respect to phase 2, we just had 3 load time series. So we just looked at them and yeah, cleaned them for some anomalies, but there were not a lot of them. So here I just plotted the chunk of data with most of them in there. So we just went through the 3 data sets and looked at suspicious parts and just highlighted them. As you can see this, like here, there are a few parts. We replaced this by missings, and basically that's it on our data pre-processing. So nothing more fancy was done here. So we kept especially all the weather data and EV data as it is. So we did not do any pre-processing with other data there. And the important part is we did not replace them by, say, most likely values, but we just put them to missing. So every information in the neighborhood might be lost as well, depending on our algorithms as well. Okay, so and after data cleaning, what we did is then we looked at the task and the objective. And this is, again, a kind of math slide, which shows what we have seen, basically. But I think it's very important to remember what is the prediction task. So basically, the load that we observe, the demand that we see, the Y, is, is just the X. So the load which we usually see plus the load of the EV chargers, which is here the Z. And there, of course, we don't know how many electric vehicles are on the grid. So we just know there is a certain number which is added. And this certain number satisfies some properties. What is important to remember is that we are interested in predicting just the daily maximum. So we have seen this. But the daily maximum is, of course, just the maximum across all the 96 quarter hours of the load. And when designing a model, we decided to design a model which predicts not just the maximum directly, but goes on the quarter hours in the first step. However, we will see this in the next slide. For designing a nice model, we basically have to remember 3 properties of the task. The first one is, of course, that prior D1, prior the first day we have to predict, there are no EV charge electric vehicles on the system. So the X is equal to Y. So we can assume this property as being important. And then we know that the number of vehicles on the grid will increase over time. So we can expect that not the function itself is increasing, but we have a tendency for increased numbers. And what we know as well, based on the sampling from the electric vehicles, is that they were sampled with preserving their weekly structure. So we have already the idea that this prediction might have a weekly pattern. However, they were not sampled with, to preserve, say, annual pattern or temperature pattern or something like this. So we know it's just about the weekly profiles and, of course, then the daily profiles of the chargers. Okay, and now the most heavy slide, I would say. What we did. So basically, the general idea is to consider an additive model because we've seen here the structure is additive as well. So an additive model makes sense. And the idea is, well, we basically have to decompose the Y into the main load and our electric vehicles, the Z's. If we have them, we can just predict them and then take the maximum across the corresponding quarter hours. So this is easy. How we did this in a more formal way. Well, formally, we defined an electric vehicle dummy, so EVD. And this is just active once we started to have electric vehicles on the grid. And before this, it's just 0. And then we designed a model which has basically two components. So we designed a model which feeds in the historic load data, and of course other external inputs, so weather data, deterministic dummies, and so on. This depends on some parameter vector. And of course we have a second component which models the electric vehicle impact. And this electric vehicle impact, of course, just depends on the dummy. So it can be only active when it's in the system, and it depends on time, so on the day and on the quarter hour of the day, which we denote by small s. So it depends on time and on the active vehicles. And of course, then we have a parameter vector θ2, which describes this part of the model. One thing we did a bit different to Jemima, what we have just seen, is we do not just have one model, but instead we decided to have 8 models. So basically, this 56 weeks we have to predict, 56 days, which are 8 weeks, we decomposed into 8 weeks, and we created 8 different models to take into account for always the most recent data in the system. So yeah, basically the last known value for predicting the first week could be already just one week ago. For predicting the second week, it has to be at least 2 weeks ago to satisfy the property here that we are not disturbed by the electric vehicles in the model. So we just take, say, clean information for designing our model. Yes, and if we have the models, of course, then it's quite easy to get an estimate for our Z. We just take the second component, we just evaluate the second part. In fact, in the implementation, we did it the other way around. So basically, we took the full model and subtracted the model with taking all these coefficients equal to 0, but this is equivalent for doing so. And if we have this, of course, taking just the maximum gives us the prediction for the corresponding day. And now the key problem is how to find the model structure F1 and F2. Jemima showed how they found already their components in the model. And we really disentangled this problem into 2 parts. The first part, where we just looked for the right components for the plane load. And here, it is feasible to train a model for each substation individually. So we just took the 12 weeks just before the EVs started to get on the grid. So basically, this was I think beginning of October. So essentially, we took September, August, and July. And for those period, we did a standard time series cross validation and tuned our model for all substations so that they minimize the RMSE. And this is what we did to find the model components F1. For the structure of component F2, it's a bit tricky because in the phase 2, we were not allowed to have multiple submissions, of course. Then we could have proceeded in the same way and just try to find better functions that describe this behavior. But of course, this is not allowed. So we had to get a feeling about the structure of the function without evaluating it. Yeah, so we cannot do some standard evaluation technique here. So what we did is we just took the structure for F2 so that it performs reasonably well for all substations on phase 1. So we thought, well, if it works quite well on all the other 3 substations from phase 1 where we could evaluate, then this should work okay for substation 2 as well. Okay, and having this, basically, you see here one model.
How to let you know, Brian, if you could try and wrap up in a minute or 2, that'd be helpful. Okay, and you see here the model with these 4 components. You see the autoregressive parts, which is just, say, for instance, the autoregressive parts of the past weeks, deterministic components, temperature components, and the electric vehicle dummy part.
yeah, so this is how those model looks like. Quite simple, just two-way tensor interactions in contrast to Jemima, so a more simple model. Here you see one of those graphs, how the results look like. So yeah, you have seen these graphs before, so we can disentangle the load into the EV part and the other ones. Yeah, we had something specific for substation 3 where we had some kind of weird values in there where we put the weights equal to 0 during the training, but that's basically it. Yeah. So to wrap up, we used generalized models. We used the manual design for the models. We had very fast models. Our models were very simple, so our training and estimation took about a second per feeder. We just used from the weather input just solar and temperature. We think it's mainly because of PV and heating effects, and we did not use any EV data. Basically, that's our solution. Okay.
Great, thank you very much. Really interesting to see that you use solar and the other team used wind and kind of like didn't see the benefits. So yeah, interesting to see some of the differences.
So at the end, it's about clouds. Yeah, the clouds which.
Yeah, maybe. Great. Thank you very much. I think we will we'll move on to the next section, kind of talking about challenge 3. So Steve, over to you.
Thank you very much, and thanks thanks to everyone who shared their slides to the two teams. I'm going to now share the third challenge. So I'm very excited about the data we'll be sharing and the challenge itself. So hopefully you can all see this now. Yeah, so I'm very interested in, so this will probably be one of the biggest data sets we've released as part of these challenges. So we're very much interested in, again, a very similar sort of problem here. You know, there's going to be an effect on the network because of more technologies and you know, such as heat pumps or low carbon or EVs, as we've seen in the last talks, as well as sort of distributed generation like wind and you know, solar and that sort of thing. So it's becoming increasingly important that the distribution networks are well monitored and that they, you know, there's a lot of visibility on those networks. And so this challenge is really about putting a spin on a kind of classic missing data problem, really. So it's about sort of, you know, can we sort of utilize sort of the wider hierarchy of a distribution network to help fill in some of this data? So yeah, without further ado, I'll sort of set the scene a little bit. So I'm sure many of you are aware, but for those who maybe not, sort of the electricity network in many, you know, sort of distribution networks is sort of very similar to this. You have a transmission network which steps down into the distribution grid, and this steps down at further substations to sort of low voltage. And you know, you have various connections, sort of maybe large industrial consumers, renewable energy sources, and of course lots of other technologies and buildings when you get down to the lowest voltage. This talk's really going to be sort of focused in the sort of grid supply point, which comes from which sort of essentially translates from the transmission to the distribution grid, and then we'll sort of step down through to the sort of the primary substation level at about 11 kV. So yeah, essentially there's a hierarchy where you sort of step down from grid supply point down to bulk supply point down to primary. So I'll just sort of outline that very briefly. What we're going to be giving essentially is one grid supply point substation data, demand data for about 2 years. And that's going to be connected to 9 bulk supply points. So that's a step down in the voltage. And then that will further step down to each one of those bulk supply points will be stepped down and will be connected to a number of primaries, and the number of primaries will vary depending on the bulk supply point. So to kind of give the specifics of the challenge, what we're going to be doing is having a number of scenarios, and each of those scenarios will look at a different combination of substations across that hierarchy, and we'll be deleting data from sort of full day based on that scenario. And I'll talk about the scenarios a little later on. By the way, I won't go into all the details on these slides because we'll share the video later, and of course you can, and we'll share the slides on the LinkedIn page as well. So if I go a bit quickly, don't worry, I'll these things will be shared anyway. Just to sort of illustrate this in a bit more detail, what we're sharing here is we've got the grid supply point, we've got a number of bulk supply points, and then they're connected to the primaries, as you can see here. So we're dropping from high voltage down to low voltage. And of course, what this means is the demand is accumulating up to the sort of bulk supply point, then up to the grid supply point. So increasing amount of demand from this level up to that level. But of course, as well, another thing, as you saw from the previous illustration, there will be some potential connections on there which we don't include as part of our the challenge. That data won't be there, so it should be aware that there may be some things like this, sort of maybe primary missing, maybe some consumers missing, maybe some demand side generation missing. Okay, so we're as I say, there's 8 scenarios, and they look at different combinations of where we create the missing data. So another thing is there's going to be further details on the CodaLab page where we'll host the competition. So there's a lot more reading on there if you need further details. But essentially, we can look at things like scenario 1, where we delete the same day from all of the substations. We'll then have others where we sort of just delete data from a single level, like scenario 4, which removes just all the 1 day from the bulk supply points. And scenario 8, say, where we'll delete the data from 10 primary substations, which will be across all the BSPs. And then others where there'll be some across the levels as well, a couple of levels, like scenario 6. So I guess one thing just to sort of help you with the challenge is you may expect that actually something down in the lower level will aggregate up and match the bulk supply point. I've already mentioned that might not be the case because not all the demands on there or generation on there will be known. But on top of that, there'll be electrical losses. So the demand, not all the demand makes it to the sort of bulk supply point and further up to the grid supply point. So the total demand at the primary won't necessarily match the total the demand measured at let's say, the bulk supply point. And another complication is obviously there's switching where load is diverted from one area of the network to another. We've tried to make it a bit simpler that we don't include that within the missing data part, but of course, keep an eye out for that, and you may want to look at the data and adjust in that case. I won't go into this slide in detail, but just to sort of say, we're going to be doing the similar thing to the previous challenges in that we're looking at a skill score. So it will be a relative score for your estimate, and we'll scale that according to sort of the benchmark score as well, which in this case, a benchmark will just be assuming that the missing values are identical to the values from exactly the day before. Okay, but essentially all we're doing is we're taking for each scenario, we're going to group them into 3, into grid supply point, bulk supply point, and primary. And for each of those groups, we then measure the sort of RMSE error, so just the squared error between them. But because then we want to join up this data from different areas, so grid supply point, bulk supply point, and primary, they'll obviously have different levels of demand. So to make that fairer to compare, we're also scaling that with this with the mean demand of that group. So it'll be the mean demand of the primary, mean demand of the BSP, or mean demand of the grid supply point. Okay, and that combines to make an average, which is then scaled according to the benchmark score. So yeah, I've already mentioned the data really, but we'll be providing 2 years of half-hourly data for about 40 substations. I should say there are some missing data and anomalies in there, and some substations are better quality than others. But of course, we're only going to be testing on the missing value in good quality areas where the data is complete. Otherwise, you can't calculate the errors. All the data is in UT timestamps, so that means you can combine it with the provided weather data. And the connectivity and what primary substations is connected to what bulk supply point. That is all on the CodaLab page, which we'll put all the links in the chat as well. And yeah, so this is where it is. So if you've been to the UK or you've been to Bristol, where it's all going to be around that area. So you can also find a bit more information on the network capacity map if you're interested. Example of some of the profiles. Obviously, these aren't test periods, but what you can see is the data gets a lot less smooth as you go down from grid supply point down to primary. Weather data, I won't go in loads of detail with this one again, but we're again providing actually the same sites as the previous one, which are at particular locations. Again, it covers the period we're interested in, the 2 years. It's all in UTC. It's the Merritt-2 reanalysis data. as with the previous challenge, you're free to grab more weather data if you like. And you are allowed to use other data sources as long as we check it first and it's public data and the licenses allows it to be shared. Again, I won't go into this, but we're sharing sort of the 6 different variables for the weather data. And that's just an example of the weather data itself. Okay, yeah, so a little bit about the challenge. Like the other challenges, it's going to be 2 weeks for the practice and evaluation. We'll actually allow the practice session to carry on, as we saw in the previous chats, that people still wanted to evaluate on that as the evaluation phase is running. So you're free to keep practicing if you wish. But the only 2-week period that will count will be the evaluation one. Actually, we're slightly longer than 2 weeks in this case. So it'll be to the end. It starts today, but then on the evaluation phase, we'll start on the 30th of March and run just slightly over 2 weeks. The scenarios will be 8 scenarios, and they in total provide 14 days where they'll be missing data. And as I said, other data is allowed, but you've got to check with us, and all the suggestions must be done by sort of 2 days prior to the end of the practice session. And then we'll share that with everybody. And as I mentioned, the CodaLab page will be used as the platform. Some of the rules, as always, we only allow teams of up to 5, and in the final evaluation phase, only 6 submissions are allowed, and we ask that only 1 person from each team submits in that, so that we can keep track of everything. Yeah, and the prizes, as usual, we're going to award £500 to the winner. We then would ask them to contribute a summary of their method if they wish to the final report, and that way we can sort of show sort of the benchmark methods out there. Also, then we'll run in a session like this where the top 2 or 3 teams will be asked to present, and we'll obviously award certificates for that. And finally, as ever, we'd like to, if people could share code, because we want to sort of demonstrate the methods out there and help people just pick them up and maybe improve them, or show sort of the state of the art that is out there, really. So we'll ask if anybody would like to share by the end of the competition their code, and we'll provide a sort of high-level code review of that as well, as we did in the last one. Okay, so I hope my colleagues sharing the links and everything in the data set. We should actually made the challenge link live. We'll just check that is the case. But if it is, then it is now live. So you can start straight away if you wish. And if you want to get the data, go to the WPD Data Hub, and the weather data will be on the CodaLab page. So in the WPD data, there's also a template. So we ask that you use that template to submit so that everything works out within the evaluation functions. Finally, if there's any questions, as usual, feel free to email us at that email address. And we also respond through the LinkedIn challenge forum. Please join that if you haven't already. It's a great way for people to interact, and some people form teams on there. And we'll also share all the resources on there as well. So shortly after this presentation, we'll share the slides and the video link. Yeah, so as I say, just repeating the dates there, use the template. As I say, the practice session has unlimited submissions, so please use it. And please use the LinkedIn forum. Just finally, there's a couple of slides at the end just on sort of helping you with CodaLab if you've not used it. So when we share the slides, then you can look at that if there's anything you have questions about. But otherwise, feel free to sort of ask us. So that's it from myself. I'm happy to then answer any questions if anybody has any about this, or feel free to ask questions for Florian, as I know we didn't have huge amounts of time there. So yeah, any questions about the data I can answer. We've also have Liam from WPD on the line, so he can ask any questions you might have about that data. But if there isn't anything, then I just wish you all really good luck with it. And yeah, feel free to send us any other questions you may have. Brilliant. So I think that's it. So yeah, thanks a lot, everybody. And yeah, good luck with everything. And yeah, please keep in contact.
Cheers all. Ciao now.
Thank you.